We're going to build a garden room as a home office, and it's going to look something like this. We wanted a room that was roughly 10 meters squared. We thought this was a generous size for a two-person office without using up too much space in the garden. We found searching for a garden room supplier to be a minefield. Many structures were little more than glorified sheds, whereas the true garden room suppliers had somewhat misleading claims about quality, and the initially advertised price was rarely the true price of a fitted structure. But after a lot of digging, we found that for a similar sized structure to what we were looking for, it would cost somewhere between £8,000 and a whopping £25,000. After doing some quick sums, we think we can build a high-end garden room for the lower end of that price range. So we're going to jump in and we're going to give it a go. We're going to film the entire process, and we're going to let you know the materials we use, the techniques we use, the mistakes we make along the way, and the reasoning of why we're doing it that way. And at the end of it all, we're going to put together a set of plans, so if you like, you can build along with us. Now, I realise many of you want to get straight to the build, and if that is you, we have chaptered the video down below, but I think this bit's really important. The design is initially going to be governed primarily by planning permission, or rather what we can design without planning permission, i.e. permissible development. When digging into the permissible development rules, the key takeaway for our purposes are that in England, no part of the building can exceed 2.5 metres if within 2 metres of the boundary. If more than 2 metres from the boundary, then you cannot exceed 2.5 metres to the eaves. Now, the eaves seem to be a somewhat subjective term, but in this context, I believe that means to the bottom edge of the roof where it meets the outside wall. Here in Scotland, the rules are a little easier to interpret. They state that the building can't be more than 2.5 metres tall unless more than 1 metre from the boundary. Then it can be 3 metres tall to the eaves. There are of course other limitations, but they're more specific and not relevant to us at this point. Still, it's worth reading up on them, so if you are building an outside structure, I'll link the rules for both England and Scotland down below. The 2.5 metre limit will become fundamental to this build. Basically, every off-the-shelf garden room will be below the 2.5 metre limit, and it pretty much defines what a garden room is. Anything above 2.5 metres tends to need planning permission, and it's a whole different kettle of fish. Now, 2.5 metres might seem reasonable, but it's actually very restrictive. It's hard to make a nice looking room that's well insulated and has enough ceiling height inside. The plan is to build a garden room in the corner of the garden and more than 1 metre from the boundary. That means here in Scotland we can legally make the buildings 3 metres tall to the eaves, but since we'd like to make this guide applicable to everyone, we're going to design around the 2.5 metre limit. Although we will keep our options open in the future to exceed this. Also, if you're building on a sloped surface, it's worth saying that in England you measure from the high point of that slope, on Scotland the low point. At the end of this, the building will be classed the same as a shed or a greenhouse, so it doesn't need to comply with any strict building standards. That being said, we want to build a quality structure, so it makes a lot of sense to pay attention to these standards as they provide a lot of good guidance. The next step in the design process was deciding on the overall proportions of the room. We wanted to fit in 2 large desks while still having space to move around. On top of that, we wanted to work with standard material sizes so we could be as efficient as possible. In the UK, we seem to be in an odd situation halfway between a metric world and an imperial one. This can complicate things when sourcing materials. For instance, plywood tends to be sourced in imperial measurements, whereas OSB tends to come in metric measurement. This can have implications throughout the build, but on the whole it seems best to design around a metric standard. After much thought, we decided to go for a floor size of 4.2 by 2.4 metres. These dimensions make full use of the board lengths and require 3.5 board widths. This option creates a stronger frame with fewer joints and less wastage. As for the rest of the design, we've already planned that out, but here's a sneak peek. There are many different foundation options with no single best solution. However, again, the primary design limitation is the 2.5 metre overall limit. This means we can't use any foundation that raises the floor more than necessary. We also need to account for an air gap between the ground and the frame of at least 50mm. This is to allow for air movement beneath the building, which is essential to keep the building healthy. Ideally, this distance would be more, but it simply isn't possible with the height restriction. It's now a good time to consider how the dimensions will stack up and show why every millimetre is important, but to do that we need to know what timber to use for the floor and ceiling joists, and for that I look up a floor joist span table. These are tables that list how far a joist can span for a given profile and joist centres. These tables can be found online and I'll link this one down below. I know that we'll be using C24 regularised timber with 400mm centres. I also know that my joists will need to span around 2.2 metres with our frame design, and I want to find a timber with the least depth while achieving that span. In terms of dead loads, we can go for this column because we're not going to have any permanent weight, such as walls, resting across the span of those joists. It's worth saying you get different grades of timber, C16 and C24 being the most pertinent to this conversation. C16 tends to be cheaper and more readily available, but with more defects it's also a weaker timber. When I look at the C16 span table, these are the suitable joists, but they're all deeper than I would like. When I look at the C24 span table, these are the suitable timbers. I'm going to go for this one because it's strong enough and has the least depth. It's worth noting that these dimensions are the finished dimensions you need for the timber, that is, the dimensions you'd measure with a tape measure. Confusingly, some timber yards like to list the nominal dimensions of the timber or the rough cut size before it's planed down to thickness. Now knowing the joist depth and assuming the same joists for floor and ceiling, we can look at how the dimensions stack up. 50mm for an air gap, 120mm joist, 18mm OSB floor, 2100 ceiling height, and then assuming a cold roof setup, we have 120mm joists again, 18mm OSB, and 21mm of roofing material. That equals a total of 2447mm. This is clearly a simplified example, but you see why we need to be so careful with our dimensions. When considering the different foundation options, I found this website to be a great resource. I'll link it down below. Among my top choices were a concrete slab. This is a great option, especially on flat ground like ours. Floor joists can lay directly on the concrete, and because it's a solid platform, the joist depth can be reduced. But concrete is expensive to lay at about £2,000, and if not perfectly flat, then it can prove difficult. For us, the cost was just too much. Another good option is plinth foundations. These are preformed concrete feet that the frame sits on. If sunken into the ground, they can keep the frame low-ish and provide a solid foundation. They are, however, expensive at around £1,000. I've also seen this done in a more DIY fashion using breeze blocks, but levelling these sufficiently can be extremely challenging. Ground screws are a fashionable choice and for good reason. They can support a lot of weight and are relatively easy for DIY installation. Getting an even height is as easy as screwing them a little deeper, and they can sit low to the ground. They're also a great choice for sloped ground. At roughly £500 for a DIY install, they are the cheapest option so far, and an option we were tempted by. The option we chose, however, is not often considered, and I'm not sure why. When we put our shed up, it was on very uneven ground, so we supported it via wooden fence posts set into concrete piles. This is easy to install, and it was very cost effective. The only reason I can think it's not popular is because the wood can rot over time. But exchange that wooden fence post for a recycled plastic post and all concerns of rot have gone. We consulted a professional about this and they confirmed to us that it's a viable and good option. All in all, it's the cheapest option at around £350 and it should be the easiest method to install. After a great deal of thought, this is the design I came up with for the foundations and timber frame. I wanted to maximise material efficiency while looking for an easy build and a solid structure. With 15 posts total, this equates to roughly a post every metre. I contemplated 12 posts, as by some reckoning that's still plenty, but with advice generally to go between 12 and 15, I chose the cautious approach and went for 15. Unfortunately for my compulsive need of symmetry, this meant the posts couldn't be equispaced unless I chose a frame design more like this. Some like this design because it reduces the potential of bounce in the floor and transfers the forces better. While this is good advice, I felt the benefits would be very little in this situation. This is a much smaller structure than a house, the loads on the floor will be relatively low and the majority of those loads will be around the perimeter. Also, with 3 posts in the centre, I cannot foresee any bounce. There would also be stages of the build where this design would be much more troublesome, installing the joist hangers in this small gap for instance. With this design, I'm able to be more material efficient and have a simpler layout for the insulation and flooring. All the insulation and noggins can be cut to the exact same width, except for the outer pieces. This should allow me to batch cut the insulation and will be both quicker and more accurate. Also, with this design, I can go for a flooring pattern like this. With fewer joints, the structure will be stronger, and again, it will be an easier build. And lastly, there are double joists on the outside to increase the strength and distribute the load. It also provides a more substantial platform to screw down into later in the build. As for the rest of the design, it's going to look something like this. But I don't want to get into the details right now because, well, we've changed our minds. Although this design was based on another design that we liked, we realized that it's not going to be practical as an office, so we'd like to tweak the location and size of the windows. Also, we realized that we can make the building bigger and more insulated for free. Our thought process and how we can achieve this gets a little complex, so rather than getting into it now, I thought for clarity it's better that we tackle that when we put up the walls and the roof. And that's the design complete as far as I have it. In the next video I'll dig the foundations and simultaneously build the frame. I'm a little further ahead with the build than I am in my video releases, so as soon as I have enough built that I'm confident in the design, I'll release plans so you can build this with me. Those, along with key links I've mentioned in the video, will all be linked below. So stay tuned, there's lots more to come from this series, and until next time, cheerio!